So let me also start by thanking the organizers for organizing this very nice conference and also giving me the opportunity to present some of our recent results. So right at the onset, let me acknowledge the people with whom this work was done with. So Nesta was a PhD student who graduated a few months back. And Orko was a very excellent postdoc who has now moved to Würzburg for another postdoctoral stint. And in one of the projects, we collaborated with Professor Ajit Balram, who is at IMSC in Chennai. And at ISC, we have the opportunity to work with and learn from absolutely stellar undergraduate students. So 3 of them worked on the projects that I'm going to show here. Shashwata, who's now at Cornell, Dominic, who's now at Minnesota, and Shomadeep, who is now at Maryland. So they're pursuing their grad school in the US now. All right, so just to remind you, of course, we are all very familiar with the notions of Berry phases or Panchratnam Berry phases. So if you take a quantum state and you evolve it in time, there are different factors, phase factors that can arise. One of them is, of course, the usual one, which we learn in quantum mechanics 1, which is just you take the energy eigenvalue, you multiply by or integrate over time. On the other hand, there's another phase that can arise, which is the geometric phase. So if you have a slowly moving variable in time, you can write it such that the time dependence actually goes away. So R is your parameter. So in a solid state system, it could be your momentum, for instance. And this sort of geometric phase factor was first seen by Pancharatnam, and then many other people built on this, including Longway-Higgins and others. And eventually, it was put in a very general framework by Michael Berry. And using this object, one can define what is called a connection. So a Berry connection, which takes this form, where you sandwich the gradient operator between the state, and you can take the curl of this object and define a curvature. So this is like a vector potential in the whatever space you are, the R space, and this is like a magnetic field in that particular space. All right, and as we know, this Berry curvature has enormous ramifications in many phenomena in condensed matter and other physical systems. So one of the most celebrated ones is, of course, the quantum Hall effect, where, just to remind you, those of us who are not familiar with, if you take a 2D electron gas and you apply a magnetic field in the perpendicular direction, and then if you're at low enough temperatures and the fields are high enough, then you see this, if you look at the transverse conductivity, that has these very nice, perfectly quantized plateaus. And this happens because of the Berry curvature. So if you calculate the conductivity, then it has this form where E and H are, of course, the fundamental constants. Epsilon ABC is the Levi-Civita tensor. And you take the Berry curvature multiplied by the occupation function F0 and integrate over the Brillouin zone. Okay. The key thing here is that one needs to break time reversal symmetry, which is provided by the magnetic field in this case. Or you can have a quantum anomalous Hall insulator where there's some intrinsic magnetization which can break the time reversal symmetry. Now, one of the questions that was asked by Soderman and Fu around 2015, building on some of the older work from Orenstein and Moore, was that can one get such an effect, a Hall-like effect, without breaking time reversal symmetry? And it turns out that the answer is yes. And what they showed, essentially using Boltzmann-like theory, that you can get a second-order response, which looks something like this, which, just to remind you, if you remember this conductivity that we get from the Berry curvature, this response also looks very similar. You have some prefactors. There's the Levi-Civita tensor. And then you take the derivative of the Berry curvature multiplied by the occupation and integrate over the Brillouin zone. Okay? So it is very similar to the response that we get from the Berry curvature, except that the prefactor in front is not universal. These are not fundamental constants. So this is the relaxation time tau, and omega is the frequency at which you apply the field. Nevertheless, there is a transverse response, just like the Hall case. But you have to go to higher order. You cannot remain in the linear order response. Okay? All right. So the key quantity that describes this kind of a higher order response is something that they call the Berry curvature dipole. So that is defined in this way. It's a tensor, and it's defined in just as if you remove all the prefactors that I showed you, it's just the derivative with respect to k of the Berry curvature multiplied by the Fermi function, and you integrate over the Brillouin zone. So that's the Berry curvature dipole. And just to kind of give you a feel for why it is a dipole, one can actually take the integrand, the kernel here, and plot it. So the details of the model for this are not very important. but you can just plot this object, and it has these, so positive and negative are denoted by red and blue colors. So this distribution looks like a dipole, therefore the name is a Berry curvature dipole. And you can in fact generalize this to higher order moments. So you can have a Berry curvature quadrupole and so on, right? So this was not merely a theoretical idea, and very soon, within 3-4 years of the predictions from Sordeman and Fu, there were these beautiful experiments from the Cornell and the MIT groups, where they showed that in bilayer and few layer WTE2, which is one of the transition metal dichalcogenides that we have heard about quite a bit, there is a nonlinear Hall response. So the experimental setup looks something like this. So you have few layer WTE2 sandwiched between top and bottom gates, and the device has multiple terminals, and what they did was they measured the voltage response at frequency 2 omega, because we have to go to a nonlinear response when the current is applied at a frequency omega, right? And what they saw basically by doing various combinations of the voltage and current terminals is that the predictions, the results were in line with the predictions of Sordeman and Fu, and one has a nonlinear voltage response. And since then, there have been a bunch of material platforms that have been identified where such an effect arises. For instance, this very nice work from the TIFR group, where Professor Agarwal did the theory. You cannot escape Professor Agarwal's name in this session. So they take twisted double bilayer graphene and found suitable geometry to actually induce this kind of a nonlinear Hall effect that I just mentioned. Also, if you artificially corrugate graphene, for instance, by putting it over these kind of step geometries, then also you can end up with a nonlinear response. And finally, very recently, there has been work on oxide interfaces, where the classic LAO-STO heterojunctions have been shown to have some kind of a second order response, but this is at quite low temperatures. And these are just some of the very few examples, selected examples that I'm showing you. And if you're interested, you can look at this review that we had the opportunity to write, where there are many other examples that we discuss, and also the theory. Okay, so in today's talk, what I'm going to do is tell you two little short stories where we have thought about or tried to apply these ideas. One in chiral materials to show how the response varies between two enantiomers, so left and right enantiomers, and the other one, depending on the time, I show how in perovskite oxide superlattices, depending on the thickness of the oxide and the kind of elements there, one can tune the nonlinear Hall response. And one caveat here for specialists is that I focus only on the intrinsic contribution. I don't talk about disorder and other effects. Also, I talk only about the Berry curvature dipole response. Now it is known that other quantities like the metric and other objects can also give you a nonlinear Hall response. But I'll focus only on the Berry curvature dipole intrinsic response. All right, so let's start with the chiral systems. Just very briefly, so we all of us know what chirality is. So essentially, if an object and its mirror image are not superimposable on each other, then the object is said to be chiral. And of course, as we know, it is widespread across physics, chemistry, biology, and everywhere. For instance, life, it is conjectured that there might have been some asymmetry to begin with, which might have resulted in the DNA having a particular chirality and not the other one. Okay, what about in solid systems? So crystal structure is said to be chiral if the space group has only what are called proper operations, so only rotations and translations. Then in that case, one calls the crystal chiral crystal. The classic example, hydrogen atom-like example, is the elemental tellurium. So if you look at this structure here and imagine these atoms going into the plane, then they have one chirality or one sense of rotation for one enantiomer and the other sense of rotation for the other one. And you can try to play around with this structure, but you'll never be able to superimpose the two structures. Okay. So it turns out that inversion, mirror plane, roto-inversion, glide are what are called improper operations. And a number of different aspects of chiral materials have been recently discovered. For instance, chiral phonons, ferroelectricity in chiral materials, and interplay of topology. So the question we ask is, what about nonlinear Hall effects? Since you have low symmetry, you have broken, a lot of symmetries are not allowed. So what would be the effect on the nonlinear Hall effects? Okay, so we start with a very simple model, which is sort of inspired by graphene and DNA in some sense. As the previous speakers already showed, if you have this kind of a honeycomb structure, you have some hoppings. But in this case, what we do is to break inversion, we actually make the nearest neighbor hoppings unequal, right? So there are some T0, T1, and T2 shown by different colored bonds here. And then we kind of have the two enantiomers in some sense by having the hoppings activated between one set of sublattice and the other for the left and right enantiomer. That's the next nearest neighbor hopping, which gives a handedness. So if you can write down the Hamiltonian for this case, so Tij is the nearest neighbor hopping, and it's unequal between the nearest neighbors. And then there is this chiral-like term which occurs only between the same sublattice and is absent for the left versus right. And this together they break inversion and give you the chirality. So what we can do is we can go ahead and for this model toy system, we can calculate the Berry curvature. And here I show you the energy bands of this system. And on top of that, I have superimposed the Berry curvature. So red here means positive, blue means negative. And this is for the left enantiomer. So you see that near the band edges, which is what also Avik showed, that where the band gap shrinks, you have large values of the Berry curvature. And now if you go to the right-handed enantiomer, you see that this is exactly flipped. So what was blue here has become red here, and what was red here has become blue. So the two enantiomers have opposite distribution of the Berry curvature. So what about then the Berry curvature dipole or the resulting nonlinear Hall response? So it turns out that for this model, there are two non-zero components of the Berry curvature dipole tensor, dxz and dyz. And here I show you the dxz component as a function of energy for the right-handed enantiomer and the left-handed enantiomer. And I see that the sign is exactly flipped, and the same is true for the dyz component. So they give exactly opposite value of the Berry curvature dipole, but this is only for a toy model, right? So you can ask, okay, what happens for a real material? So we went ahead and did these type of calculations for more realistic materials using density functional type calculations. So one of the first materials that we looked at is NBSI2, which is chiral structurally and is the metal. So these are the two enantiomeric structures that it crystallizes in, the P6222 and the P6422. So again, you can imagine the blue spheres are the silicon atoms and the green ones are the niobium ones. So you can imagine this kind of a chain winding around into the plane for this space group and going in the other sense for the other space group. And if you look at the band structure, so this is very simple DFT GGA type band structure. The band structure for both the enantiomers is exactly the same, right? So we can go ahead and do similar calculations that I showed you for the model. So here I show you the band structure for the left-handed one, or P6222 and the P6422. And on top of that, I have superimposed the Berry curvature. Red again means positive, blue means negative. So you see a bunch of places, there are what we call Berry curvature hotspots, where the value becomes very large, and also the Berry curvature is changing very rapidly around these points. And again, if you notice, whatever is red here has become blue. So for instance, here the upper band has a positive Berry curvature, here the upper band has a negative Berry curvature. So between the two enantiomers, the Berry curvature distribution has swapped sign. And so before I show you the results for the Berry curvature dipole, one can actually look at the symmetry constraints on this Berry curvature dipole tensor. So as with any other observable, it must obey the crystal symmetries, right? So here D is the tensor of the BCD, and S is the matrix representation of the symmetry that is underlying. So one can, for this material NBSI2, one can actually do this calculation and write down all the symmetries of this crystal. And it turns out that the tensor takes this form where only the diagonal components are present and the off-diagonal ones all vanish. And in addition, there's also the constraint that the sum of the diagonal components must be 0. So trace should be 0. Okay, so then we do the full calculation, DFT calculation plus vanirization. And I have the results here. The vertical axis is the Berry curvature dipole, and the horizontal axis is the Fermi level. And all the three components are plotted here for the P6222 case and for the P6422. And let's look at, for example, the black curve here, which is the ZZ component. So for the P6222, you see near the Fermi level, it's kind of positive. On the other hand, for the P6422, it is negative. And you can figure out all these peaks and troughs that occur. Those are coming from different Berry curvature hotspots that you can track in the Brillouin zone and see how the Berry curvature is distributed. And the values, if you think about the values, they're slightly lower than what you would expect, what you get for the transition metal dichalcogenides, but nevertheless, they're finite. So what we say is maybe one can use this nonlinear Hall effect as a kind of way to distinguish between the enantiomeric pairs. Typically, one does optical experiments to distinguish them, but perhaps there are transport ways to actually distinguish between the two enantiomers. And finally, I can show you a kind of the tellurium case, which I alluded to before. So in this case, of course, we have these two enantiomer structures that I showed. And just for a technical note, that because here the band gap is severely underestimated, so one needs what is called a hybrid DFT calculation to actually get a reasonable band gap for this class of materials. So again, I show you these kind of plots. So this is for the P3121 and P3221. And whatever is red becomes blue. In addition, there are these what are called while points in the spectrum of tellurium. So they also, it turns out, have an opposite topological charge, but that's a different point. And if you look at the Berry curvature dipole components, they also switch sign between the P3121 and P3221. All right. So overall, what we learn is that perhaps BCD-driven nonlinear Hall effect can actually be a way to distinguish between the enantiomeric pairs. And very recently, just a few months back, there was first verification of our predictions in a slightly like a thermoelectric type measurement rather than an electronic measurement, where they took the left-handed and the right-handed structures of tellurium and measured the Hall voltage with temperature gradient instead of a voltage gradient. And what they did find was indeed that it is kind of opposite in sign between the right-handed and the left-handed structure. The values are not exactly opposite in their case because of their sample dependence, so there might be defects and Fermi level might be different in the two samples. But nevertheless, the overall idea seems to be verified that the two enantiomers have opposite nonlinear Hall effects. All right, so how much time do I have?
17 minutes.
17 minutes, that's good. Okay. All right, so let me then switch to the next story that I want to tell you, which is on perovskite oxide superlattices, where we tried to find out what are the conditions to get Berry curvature dipole in such superlattices. So many of us are actually familiar with perovskite oxides. So typically they form in this kind of a structure where there is a cation A, another usually transition metal cation B, and it is surrounded by oxygen, so AbO3 form. And this is the ideal cubic structure, but the lattice is susceptible to a lot of structural distortions. This could be rotations or off-centering of this central transition metal ion, and that has led to a lot of interesting phenomenology, for instance, ferroelectricity, piezoelectricity, and all sorts of magnetoresistance effects, multiferrocity, and so on, including superconductivity. So we ask the question, because these symmetries can be lowered, what would happen? Can one get Hall-like responses here in the nonlinear order? Okay, so here is what we propose to study. So we take ferroelectric insulator. Barium titanate is a well-known case, but the problem is that it is insulating, right? As all ferroelectrics are. So there'll be no transport signatures directly. So what we do is we propose to sandwich them between a metallic perovskite. So if you go to a heavier element such as osmium or iridium, so barium osmate or barium iridate, they are metallic. Okay. So the metallic layer sandwiched between the ferroelectric insulator. The ferroelectric insulator provides the lowering of the symmetry because the titanium atom off centers, and metallicity is provided by the heavier element heavier element perovskite. And since we have the same A side cation, one expects a lower disorder, reduced interfacial disorder, and so on. So right, so here is the main idea illustrated. So we need the polar distortions so that one can break the inversion symmetry. Without the inversion symmetry breaking, there is no nonlinear Hall response. So what we do is, so here are the two structures. So there's the cubic or the paraelectric one where the barium titanate is in the cubic phase. So here is here's the barium osmate or barium iridate sandwiched between barium titanate layers. And one can undergo a distortion to actually distort this titanium off center. And then what happens is, because of this proximity to the barium titanate, the central metallic layer also loses its symmetry. And this, as you can see here, this also moves slightly away from the center. So overall, in this case, one has inversion symmetry, and there will be no Berry curvature dipole. One can show that it will vanish identically. On the other hand, in the tetragonal case, where barium titanate is in a ferroelectric phase, one loses the inversion symmetry, and the Berry curvature dipole is activated. All right, so one can go ahead and do density functional calculations for this. Here are the band structures. This is for the paraelectric case. You see nice bands crossing the Fermi level, which come from the osmium state, whereas the barium titanate remains sort of insulating. And now if you go to the ferroelectric case where the off-centering has occurred, you start to see these band splittings, which is the usual Rashba splitting of the bands, as you expect when the inversion is lost. And these bands again come from the osmium or iridium T2G levels, and the broken inversion gives you this splitting. All right, so just now, by now we are familiar with these kind of plots. So here's the band structure, and on that I have superimposed the different components of the Berry curvature. And you see that around the Fermi level, in the osmium case, so this is the osmium layer 1 and barium titanate 4 layers, you see that there is a reasonable value of the Berry curvature near the Fermi level. In the iridium case, the values are smaller, but further away they exist nevertheless. So there's some possibility of the Berry curvature dipole to exist. So that's what we did. We went ahead and calculated these values from the DFT and vanirization. So here I show you the BCD, different components. So it turns out in this case there are only two non-zero components that are allowed, dxy and dyx. And if I zoom in around the Fermi level, you see the values are finite, but they're quite small, right? For both cases, for both osmium and the iridium case. So that is predominantly coming because we have very few states near the Fermi level, which gives us a relatively reduced Berry curvature and as a result reduced Berry curvature dipole. So one way that we think this could be alleviated is to increase the number of layers of the iridium material, right? Iridium perovskite. So this is a comparison between one layer of barium iridium oxide and barium titanate, and versus the two layers of barium iridium oxide and barium titanate. Now if you look around the Fermi level, there are these peaks that come up, and the value is raised by approximately a factor of 2. So the BCD overall can be tuned by tuning the thickness of the middle layer that we have. And of course many other compositions are possible. There is a lot of flexibility with the oxide, perovskite oxides. So one can think of this is just a proof of concepts, one can think of other combinations where the values are even larger and perhaps one gets even more response than what we propose here. Okay, so with that, let me summarize. So overall the story is the following, right? You can get a Hall response, nonlinear Hall response, even without breaking time reversal. This is what Soderman and Fu showed. So what I tried to tell you was, in case of chiral materials, one gets an opposite response from the two enantiomer pairs. So perhaps Berry curvature dipole can be a good probe of distinguishing between the two enantiomers. And in the second part of the talk, I showed you these examples of perovskite oxide superlattices, where one can possibly control Berry curvature dipole by tuning the composition and the thickness of these of the superlattices. And here are the references. In case you are interested, this is the review. If you found this interesting, you can look up more of the details and things here. With that, let me end and thank you for your attention.
Now questions from the audience?
So I have a question from the first part of the talk.
Sure.
So in your hexagonal lattice, the bond distance between any two sides are the same. So
Right.
how can you physically interpret the origin of these three different kinds of
Right.
fast neighbor hopping?
That's a great question. So here I showed them as similar. You can think of maybe perhaps stretching or
So is it
straining.
distorted kind of system?
Yeah, one can think of it as straining or distorting so that the three bond lengths can become unequal. And then just what Avik showed, right, by the exponential change in the hopping can result from this distortion that arises.
And out of these three different kinds of hopping, how do you consider that which one will be the higher one and then the subsequent one?
Oh, for the model case, it doesn't really matter. All I'm trying to do is break the symmetries. So, but I mean, in reality, of course, depends on how you put it, for instance, on a piezoelectric or other whatever substrate you're using, then one has to look at the details of the interface and see which one becomes larger or not. For the model, no matter, as long as they're different, you would see the Berry curvature dipole response.
And is there any possibility that it will become lower than the second neighbor hopping?
it becomes
Because
lower.
you have a second level hopping also.
Correct,
so
correct. So in this case, we did not, but I doubt, because to begin with, they are quite different. So one is 2.7, and the other one is like 0.3. So you really have to distort very, very hard, and probably will break the material by then, right? So I don't think that might not be feasible.
So is there any experimental verification of?
So there is a thermoelectric measurement where they did tellurium left-handed versus
That was Hall measurement.
non-linear thermal Hall. Yeah.
So the what I wanted to understand, will the extrinsic contributions also survive this?
Yeah, that's a good question. So I think I discussed this with you. In extrinsic contributions, some of them which go proportional to the Berry curvature, they would survive this. So they would also switch sign between the two enantiomers. So I think the side jump and skew will probably okay. What we don't know is there are other, like the metric and all, whether those would survive or not, because preliminary calculations that we have done tell us that the metric does not switch sign between the two enantiomers, just the pure metric. Now we are looking at the response from the metric. Yeah.
So to continue, so isn't a sign that signature that it's, whether it's BCD or some other thing, that your VXX must be 0? I should have only a for a C3 symmetric system like this.
Right.
Should I not have the X component of the nonlinear signal going to 0 and only the Y component? Can I be finite?
You mean for a hexagonal lattice, you mean? Yeah, so here we broke that, right?
You broke
By these unequal hoppings.
I see. So now that criteria is no longer.
That is probably not strictly true. Actually, if you have purely C3, the whole BCD vanishes, in fact. So
Which is true. I have only skewed the skew part.
Yeah, that would just.
So a follow-up question, just a suggestion.
Yeah.
Do you have any, suggestion from you?
Oh, okay.
Do you have any 2D material in mind that we can
For the
study?
chiral case?
For chiral.
There are these NBOX2, which is X is some halogen. I think those are chiral and they are also layered. What I am not sure whether purely a single layer would be chiral or not, but the stacked ones they have chiral. But we can discuss. Yeah. Thanks.
We still have time for one more question, maybe.
I was just wondering, in your very phase hotspot, that's a bit far from the fund level.
Yeah, I agree. Yeah. So the value, that's why the response is kind of small. For example, for NBSI2, if you look right, these are more or less like half an EV, which is probably not probable by transport, but perhaps one can think of other systems. For instance, in tellurium, it's not too bad. These are. For instance, one can dope here, which is right at the band edge. There is some finite hotspot. Yeah, but then this is typically P-type. Tellurium is typically P-type. So maybe it's not very easy to make N-type, but yeah, thanks.
Okay, so there are no more questions, and let's thank Professor Narayan for this
Thank you.
wonderful talk.